Hi everyone, and welcome to the second papers live session. And last week we were reading the first one of the first papers about Erlang, and this Friday we will continue to read another one. And this one was created in 1990, 1 year, maybe just 1 year after the one we have. Not 1 year. I think the previous one, 1 years after the last one we have read last week. So the name of these papers is Erlang, an experimental telephony programming language, and it has been created by Joe Armstrong and Mr. Verting. So that's a really old one. So this time I will not add some music because I think this is not really nice for the live. I will put music directly on the video I will directly put on YouTube. So anyway, let's start reading this document. So the abstract represents an experimental programming language called Erlang, which is suitable for programming telephony application. We discuss some of the requirements for such a language and introduce the language by a series of simple examples which show how both sequential and concurrent activities can be programmed. We discuss the error recovery mechanism used in Erlang together with the performance characteristic of the current implementation. So that's a good thing because I think in 1990, the first version of Erlang was already working, and the syntax just changed a little bit. But we had some things that could work, and this paper is just showing you some example of how to use it. And that's why I open just a new Erlang shell, and perhaps we will try to reproduce some of the example. Erlang is a programming language designed for prototyping concurrent real-time distributed application. It grew out of a series of experiments aimed at creating a language suitable for programming large-scale telephony application. Some of the main characteristics of the language are as follows. Robustness. In programming large systems, many small programming errors will be made. We view this as an inevitable. Sorry, I will just increase the size. Formal system and exhaustive test procedures are currently not capable of ensuring fault-free software for systems of the size and complexity of modern telecoms application. Given that error will be made, we are interested in the problem of detecting and handling those errors in such a manner that the system as a whole exhibits satisfactory behaviors in the presence of error. So here I think we have the first element of the let it crash philosophy. We need to embrace errors, and errors are everywhere, and so we need to deal with it. Real time. We will be concerned with the real-time applications. Response time are critical. In many circumstances, a particular operation must be performed within a certain time. Erlang has mechanism for expressing real-time dependency. Distributed. The kinds of application we are interested in are essentially distributed. Such systems are built from a variable number of communicating nodes. Each node operates autonomously, and there is no central or master node in the system. Nodes communicate with other nodes using some form of underlying transport medium. There is only a weak coupling between the actual transport system and the distributed Erlang system. Program written in Erlang can easily be ported from an uniprocessor implementation to a multiprocessor or multi-node implementation with minimal code change. Again, this part here is quite impressive. Just don't forget, these papers came out in like 30, more than 30 years ago. It's just crazy to read something like that, like today. Erlang provides fine-grained computational processes. By fine-grained, we mean that the computational effort required to create or destroy parallel activity in Erlang is small. The granularity of computation has an important influence on how we program. In general, fine-grained computation are preferable to heavyweight processes for telephony application, since the natural way of programming a telephony application is as if it were composed of a large number of small independent agents. Functional notation. Erlang looks like a single assignment functional language. There is a subtle difference between Erlang and strict functional language. Erlang was designed as a language for controlling real-time application, whereas control of hardware and strict sequencing of events is very important. In a pure functional language, calling the same function twice with the same arguments is guaranteed to produce the same results. However, in our language, where a function call may result in an hardware action, we cannot ensure that the hardware will always produce the same result. Erlang can be viewed as a strict functional language as a regard of computational function, those not dependent upon interaction with the real world for their success, but as a conventional imperative language as regards for sequences hardware events. That's interesting because I think at the same time, Haskell came in the game, and here Joe Armstrong and Verding just did the comparison between pure functional programming and Erlang. That's really interesting. Erlang applications are built from a large number of parallel processes. We take the view that the degree of concurrency in the application should exactly match the degree of concurrency in the software structure of the program controlling the application. Exactly match the degree of concurrency in the software structure of the program. Okay, programming in an unconstrained parallel language where every statement in the language represents a parallel activity is difficult and error prone. Within any individual process, we describe sequential behavior, but allow any number of such sequential processes to execute concurrently. The only method of synchronizing processes or exchanging data between processes is by message passing. Erlang has an inbuilt module system to make it easier to construct large systems. Quite interesting. But this part here about the concurrency is a bit difficult to understand. I will read it later. So, simple example. Erlang programs are constructed from a large number of small functions rather than give a form. Oh, just one note. Just read that. I think yesterday, or maybe Thursday, I don't remember, uh, I corrected the code in Elixir where we had a really big function, but this, this, this big function could be done in just two small one. And I think that's really important. And when I started to learn, for example, Lisp, it was not in my my way of thinking. Lisp is a really great language, like a closure and scheme. And but if you want to get rid of all the pain with all parentheses, the good way is to create really small function everywhere. And you have probably one or two main function that will call those small function. That's really important, and I think that's a way to program some things correctly, because it's easier to modify one function doing one thing well than modifying a really big function doing thousands of stuff you don't really understand. So that's really nice, and this part actually is really important, and you need to understand that when you are writing Erlang code, but also any kind of code from functional programming language, and perhaps other language as well. Rather rather than give a formal definition of the Erlang language on its semantic, we show some of the language feature by example. The syntax of Erlang data structures and variables are similar to those used in Prolog. So data structure here is interesting because last week we were talking about the Prolog syntax about records, I guess, and so that's practically the same. We start with a factorial function. This is built from two Erlang equation. So I think you are familiar with this kind of code. It looks like Erlang, except this symbol here that will say to return something explicitly. And here we have the guard. So now this pipe is now called when. We have the guard here. And this syntax is also interesting because it looks like OCaml or maybe Haskell. I don't remember if in Haskell we have maybe we have this kind of notation for the quartz part. So we have one attribution and we do the factorial loop, and when we have the last value, I think we can just multiply it and return the whole result. And so we have the definition here. So the head, the guard, and the body. Function evaluation proceeds by a form of pattern-directed function evocation. When a function is called, the system searches for an appropriate equation whose head matches the function call. Any variables occurring in the head are bound to the values supplied in the call. The guard is then evaluated. If the head matches and the condition implied by the guard is true, then the system commits and the body of the equation is evaluated. Equations are matched sequentially in the order they appear on the page until an appropriate match is found. It is an error for no equation to match. Body evaluation is sequential. The return value of the function is a result of evaluating the last statement in the function body. A statement of the form LHS equal RHS occurring in the body of the function cause RHS to be evaluated and the result to be bound to LHS. Lists are written as in prologue. Thus, for example, a function which reverses the order of elements in a list could be written. Actually, this code example, I think we can do it easily. Let me try it. Up. We'll put like that. So let's try something. Rev. Ah, it will be easier to have. Okay. Let's do that. So we have rev, and we will return rev x with an empty string. So the first one is when the list is empty, and we will return the list. So that's that's a really big difference here. I will probably need also to execute prologue shell to show you the difference between the two languages and the evolution of those languages. Okay, so as you can see, it should work. I'm not sure, but it should. Okay, papers. Sorry. Papers. Weird. Okay, well, what did I do? Okay. So this is the syntax we are using right now to reverse a string. So what kind of differences we have here? So at first we have this little symbol here, so we don't need to do that anymore. The dot here, it's usually like prologue syntax. When you are creating a prologue program, the function are not separated by this symbol, but more by dots, you know, and you create different kind of function, and those functions are stored somewhere, and when you call them, there is a kind of evaluation. So, okay, let's try with the example here, A, B, C, D, and we have the CBA. So that's working. So there is few little changes, like this notation here, and perhaps this one here. So you know we have here. But it's okay. Not that the notation, I will say po x denotes the return values on this short for quote x, where the function quote merely return its unevaluated argument. So that's typical prologue. The previous examples have shown how function can be defined using sets of recursion equation. This formalism, while simple, has considerable power, we can show some of the expressive power of Erlang by examining a simplified telephony example. The example is a dialed number analyzer. We define a function lookup which analyze some number sequences sec to see if it represents a valid subscriber number. Lookup can be defined as follows. Okay, so see if the subscriber exists, it will return the sequence. Okay, if not, it's invalid. Okay, so this same code here, we'll try to create it. Lookup one, no. Oh, this will not work. That's typical. that's typical Prolog stuff. Okay. So here, this thing can't work because I think here this code is asking for the knowledge base you can find in Prolog, but we don't have that in Erlang. So actually, I would say we can do something like that. But it will not work as expected. So this part of the code will need more modification, and there are a lot of other modification. So as you can see, you have the same notation for the returned value, but we have also the fact, because in Prolog we call it the fact. You know, this is something that will return always true if it's present, and if it's present we are returning this value. So we can do that right now, so it will lead to something that's wrong in the code. How does this work? Struct is a data structure defined recursively as follow. Easy. So nil is a struct, subscriber who is a struct, s1, s2, blah blah blah, s10 is a struct if s1, blah blah blah, s10 are all structs. The object s1, s2, blah blah blah, s10 is a 10 argument tuple where each argument represents an action to be taken if a particular digit is dialed. If we were to analyze the number sequence 2, 1, 4, 5, we would first look at the third argument in the tuple. The subscriber can dial a digit from 0 to 9. These are represented by arguments 1 to 10 of the tuple. The third argument would itself by a tuple, we would then look at the second argument in the subtree, etc. Eventually, we should arrive at a terminal node in the struct, which is either nil, representing an invalid number, or subscriber root, representing a valid user number. So this part here. In our example, we used two auxiliary function, index, which is defined thus, index n, okay, n plus 1, and the built-in function getArgs, so this one we don't have it, and struct, so I think this is also from Prolog. Let me check. No, we don't have it, so that's an internal function they probably created, or maybe nope, nope. At least it's not on in SWI Prolog, blah 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 blah, which fetched the and argument from struct. So for example, get args3 foo I B C D E evaluate to C. The non-recursive equation in both lookup and lookup1 represent boundary condition. Analyzing a sequence in an empty tree always gives a result invalid. Analyzing an empty sequence always requires the user to supply more digits. Okay, so this is here. Lookup1. And yeah, okay. Manipulation of a 10-way tree shows some of the power of Erlang for a typical telephony programming problem. Tree insertion is equally simple and is left as an exercise for the reader. Examples with communication. Erlang has primitives for creating a parallel process, spawn, and for sending and receiving messages, send and receive. To illustrate this, we take the example of a simple process that could be created to count charging pulses in a telephony metering system. Firstly, a process has record debating pulses. Oh, that's really interesting. So we have the same notation here. So we have the name of the module, counter, and this module will export a function start with 2 of arity of 2. And starts is proc counter, and we have the same notation here. So actually this is valid Erlang code, and it will change just there. So the syntax is correct. We have the receive keyword, and then we will open another instruction. And what do we have here? We have the data coming. We have kind of symbol like question mark. I don't know why. Prop bump. Okay. So this part will never work on Erlang anymore. It's impossible. So everything has changed. So for example, the arrow is just a simple arrow right now, and this syntax here is a bit weird. I don't know why. And we have pump, report, reset. So I think this is the data we are receiving directly from other processes, but I'm not sure. The function start is evaluated to start a process counter. The counter process receives either a bump message from the process proc, or one of the messages reports or reset from the process sys. So yeah, that's the message coming from other process. Okay, so those one here are other process. Okay, so this is started processes. Not that in this example we have included module declarations. The module declaration in the example causes the function start to be exported from the module, whereas the function counter is purely local to the module. Exported functions are the only function which can be accessed from outside the module. A set of such a counter process could be started as follow. Same notation, same syntax. The next part is it's really like Erlang code. Perhaps not this one here. This is still prolog notation. So when we are spawning something, we are not using this syntax anymore, except if counter start will return a fun, for example, a lambda function or something like that. Same here. This is prolog notation as well. So spawn here will probably evaluate this string in another process. The function cstart init, when evaluated, spawns max line handler processes and connects to each line handler process, a process to count the number of charging pulses sent by the line handler process. Note that under intermodule references require fully qualified names. Thus, we refer to counter start within the module cstart, but simply start within the module counter. A flexible message passing and process spawning mechanism provides convenient frameworks in which simple fragments of a telephony program can be expressed. For example, we can illustrate part of the code for conventional pods, like application. So a pods, I think it's a device from Ericsson, created at this time. Pods, Ericsson. Not corruption. No, I don't think I will find something, but I think it was a device from Ericsson at this time or something like that. The code describes the situation which occurs when a call is being set up. We assume that the calling or a subscriber has dialed a valid number and the called or B numbers was free. In such circumstances, the caller will hear a ringtone and the called subscriber's phone will be ringing. This situation can be described by a pair of communicating functions, ringing underscore A and ringing underscore B. Okay, so this notation to send something to another process is the same today, but still this communication here is not working. But I probably know why. Because this is a bit like registered processes, and because Armstrong here was using Prolog, he was dealing with the isolation based on the bounded variables, and he's using that as name, I guess. So that's why we have this kind of syntax. Because if you can have unassigned variables in Prolog, and yeah, it's probably because of that. We'll see later. Maybe he's explaining that. The A side of the call evaluates the function ringing underscore A. The B side, ringing underscore B. Okay, from the A side's point of view, three things can happen. The A side can stop the call attempt by going on hook the message unhook is received from the process A, the B partner can answer the message answered is received from the process B. Our timeout can occur. After 10 seconds, the event's timeout occurs. The Erlang syntax used to express this is receive 10. Okay. So I think this is a timeout 10 seconds. And we have unhook, answered, timeout, where three dots represent the code to be executed if the condition is true. Okay. If an unhook message is received, so this syntax is wrong in current Erlang. So if you want to do after something, you need to do something like that. Let's call it timeout. We have receive, we have the pattern we have to do, so say okay, and then we have after, for example, 10,000 because we are using millisecond by default, and timeout. So that's the code we are using right now in Erlang. So this part of the code will not work anymore. If an unhook message is received, the ringtone that the calling subscriber hears is stopped by sending the message stop tone to process A. And the message is sent to the call partner to abandon the call attempt. Finally, the function idle A is evaluated. If the call partner answers, the ringing tone is removed and the switch starts. The call is now in progress and the function conversion underscore A and conversion underscore B will control future progress in the call. One further point to note about the receive primitive is that it is selective. That is to say, it takes the first message that matches from a queue of messages that are waiting for the attention of the receiving process. It is also queues any unmatched messages. So this one here, this is the same behavior we have in Erlang process currently. When we don't match a message, the message will just wait in the queue, in the mailbox. In our previous example, the process which was evaluating the function ringing underscore A was expecting one of the messages unhook or answered. Any other messages which arrive at the process will, while it is waiting, will be automatically queued for future processing. For example, suppose the following messages have been sent but not yet received to a process. Eventually, they end up in an input queue to the process. The notation P M means there is message M from a process P in the input message queue of the process. P1 on hook is the first entry in the queue. A receive statement of the form receive blah 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 will remove the top item in the queue, whereas receive ID blah 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 will remove the third entry of the queue, binding the variable ID to P3 and digit to 3. Why? Okay. After the reception of this message, the state of the input queue will be P1 on hook, P2 off hook, P3 digit 4. The selective behavior of receive is intended so that Erlang programs can easily model CCTT SGL specification. In SGL message reception, unwanted messages can be saved for later processing. The mechanism is implicit in Erlang. The advantage of embedding a fairly sophisticated message reception mechanism in the language frees the programmer from worrying about what to do with messages that should be processed at a later time, a common problem in telephony programming. This mechanism also avoids some of the deadlock problem which occur in language like OCaml, CSP, or Parlog, where an unexpected message can permanently block a communication channel. Error detection and recovery. Erlang provides a sophisticated error detection mechanism. The purpose of the error detection mechanism is to allow the system to take certain default actions in the event of an unplanned event. Using the error detection mechanism's program can be written to build a system which can restore itself to a safe state in the event of certain classes of error. The error detection mechanism provides a method whereby one process can monitor the behavior of another process. If the monitored process dies, then the monitoring process is informed. It can take action to protect the system and restore it to a safe state. So here we have the first bricks for the supervision tree. Because the basic mechanism, the error recovery mechanism used in Erlang can be described in terms of two concepts: process links and exit signals. During execution, processes can establish links between themselves and other processes. The set of processes to which a given process is linked, we call the link set of process. If a process terminates abnormally with a runtime error, then on termination, a special exit signal is sent to all the processes in its link set. If a process terminates normally, then an exit normal signal is sent to all processes in its link set. On receipt of an exit signal, the default action of the receiving process is to terminate and send exit signal to all the processes in its link set. An exception to this is when the signal exit from normal is received. Such a signal is simply ignored. The default handling of exit signals can be overridden to allow a process to take any required action on receipt of an exit signal. In the following example, evaluating the function init creates two processes: the child process, which is evaluating the function driver start, is linked to the parent process, which is evaluating the function monitor. Okay, init process flag trap exit yes. I think we have the same notation, except this is not yes anymore. I think it's true. Spawn link, this is practically the same, except we are not using driver start, but we are using fun or module function name and arguments. Monitor, okay. Spawn link is an atomic command equivalent to spawn immediately followed by a link command. This is to prevent the situation where a process can die before it is linked, so that the parent process never sees the exit signal. Process flag trap exit yes is a command which, when evaluated, tells the system to allow this process to treat exit signals as if they were normal inter-process messages. They can be received within the receive statement. Okay, so this thing here. If a runtime error occurs in the child process, an exit signal will be sent to the parent process. This will be trapped by the parent process since it has previously issued a process flag trap exit yes command. ID will be bound to the process name of the daughter process, and Y will be bound to a term describing the reason for the exit signal. Okay. This is still a prolog-like system. So, yeah. A robust server. The following example will demonstrate how we can construct a robust device allocation process. Let us suppose that we have a number of resources represented by processes which are allocated by a common device allocation process. The top loop of the device allocation process can be written as follows. A lot of code here. Okay, so the top function will wait for a message, alloc, and release. So the first step, it will allow some memory, I guess, or some devices, and the release will just remove the resource from its state. Top alloc, yes, no, okay. I think we have the first concept of the the tuple with OK and error here. We have the no and we have the yes resources. In error, in Erlang we will use something like error, no resource available, for example, and OK resource. A process that wishes to reserve one of the devices being managed by the device allocation process send the message alloc to the process and wait for the reply no, indicating that no resource is available, or yes process indicating that the process has been allocated to the requesting process. When the requesting process has finished with the resource, it sends a message release resources to the resource allocation process. The resource allocation process maintains two lists, free list of the free processes and allocated list of resource ID pairs, which remember which resource has been allocated to which process ID. Such a server will work correctly if we can guarantee that the client processes obey the client-server protocol. In other words, we must guarantee that the client process releases the reserved resources when they are finished with them. Let us now suppose that a programming error occurs in the client process. In such circumstances, the client may terminate abnormally and therefore not send a release message to the allocation process. This situation can be handled with the following modification to the allocation process. That's a huge part of code to explain, but I think they will explain it after. In this example, we have modified the previous code so that when a resource is allocated to a client process, a link is created by evaluating the link ID function between the client and the resource manager. If the client releases the resource in the normal manner with a release message, the link is removed by evaluating the unlink ID function. Yeah, just here. If the client terminates without releasing the resource, then an exit signal is received by the server. Not that it must have previously evaluated the process flap drop exit yes function. The server establishes which resource was allocated to the terminating process by examining the location list with the function lookup and release this resource for future use. In addition, endings between the client and server are automatically removed. Error kernels. In the previous section, we showed how to construct a robust device allocation server. This server should function correctly in the presence of programming errors in the client processes. This led us to the observation that not all code in a large system has to be correct in order that the system as a whole should provide acceptable behavior. By acceptable, we mean that at some level, the system can protect itself from minor errors. An extension of this observation led to the concept of an error kernel. The error kernel we define to be the smallest part of the system which has to be correct in order that the system as a whole should provide acceptable behavior. One of the major goals of system design should be to isolate the error kernel and to program it in as a clear manner as possible so as to increase the probability that it's correct. Formal tools and proof procedures then only need to be applied to the code in the error kernel and not to the entire system. Empirical studies, not described here, have shown that the error kernel for a system comprising some tens of thousands of lines of Erlang codes can be as small as a few hundred lines. Several Erlang interpreters have been written in various prologues and ported to a number of different machines. VAX, Sun, PCIe. These interpreters have been used to control experimental hardware from the Ericsson MD PABX system, which is connected to a network of Sun workstation. Distribution is provided by using the MD hub switch. The performance of the current interpreter has proved adequate for experiments in telephony programming. The purpose of this experiment was to evaluate Erlang as a programming language for programming telephony application. In this evaluation, we were interested in clarity of expression rather than performance. Future implementation will concentrate on improved performance. We are, for example, investigating how Erlang can be compiled to a flat concurrent logic programming language, such as Trend or KL. That's interesting. So we have an implementation of Strand. Strand is an open source implementation of the identically named parallel prolog dialect as described in the book Strand, New Concept for Parallel Programming. Ho 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 ho. Another book to read. And the next one is KL prologue. I don't know. Kernel language 1 is an experimental and KL0 developed by blah blah blah. Sequential logic programming language based on prologue. Okay. Interesting. So let's read the conclusion. We have presented a language designed for building prototypes of concurrent real-time robust distributed application. The language is free from side effects and contains mechanisms with which robust systems can be programmed. An explicit notion of concurrency and an inbuilt error handling mechanism allows many of the problems encountered in interaction between a language and conventional operating system to be avoided. We wish to acknowledge the valuable contribution of Björn Doker, Goran, I don't know how to say that, Anders Gustafsson, Per Edeling, and Mike Williams to the language. We also wish to thank the users of Erlang, whose patience, enthusiasm, and tenacity has never diminished, despite many non-backward compatible changes to the language. So, I have new books to read. This one, I need to read it. And Ian Foster, I think that I know this guy. I already read something from him. Okay, I think this one, designing and building parallel program. This is not available anymore. A lot of things to read. Okay, so new thing to read. We push that directly on Discord. Papers. So this one here, and I will need to read this book here. Let's check this one as well. I think I will have a lot of book to read. And this one is Big Data and Social Science, Data Science Methods. Don't really care about this one. And this one here. Okay, up. So I think it's over for today. We have read one of the first paper again on Erlang. This one was describing how Erlang was working, how to write Erlang code. I think we also saw that the old code is not really compatible with the new one, but it's working. I think with just a small modification we can have it working, and I think it could also work a little bit with prolog system. So that's I think this paper is coming just before the big transition from prolog to Erlang. I think one day in the Erlang creation, how to say that, a transition was made. They probably decided to say, okay, we can deal with this complexity and all this stuff with Prolog. It's too slow. It's probably annoying, and so they just say, okay, we will create a full language from scratch with its own syntax and own rules, and just take some part of the syntax from Prolog. Anyway, it's done for today. Next time, another papers. And I think I will try to find this book and start to read it. Or at least just read some chapters of it. But it's good, and for your information, I think this one here, I can't find it. So if someone has it in its computer, I don't know where, in paper, it could be really nice to have it and to read it. I would really like to read the Phoning Philosopher's Problem or Logic Programming for Telecommunication Application. I think that's a really important paper, and I can't find it even on, yeah, anywhere. I can't find it. It's frustrating, you know. So yeah. Anyway, it's over for today. See you next week for shortcut session, and have a really great weekend. Bye everyone.